So today we're going to wrap up what we've been saying about the technical definition of the limit, or precise definition of a limit, and then branch into talking about the limit laws, which will allow us to not really have to think so much about the technical definition. The main thing that I want to do is I want to introduce the technical definition of a left-hand limit and a right-hand limit. So we will say that the limit as x approaches a from the left of f of x is equal to L if for any epsilon bigger than 0, there is a delta bigger than 0 such that when a minus delta is less than x is less than a, the absolute value of f of x, whoops, that's not an x, minus L is less than epsilon. And we will say that the limit as x approaches a from the right-hand side of f of x is equal to L if for any epsilon bigger than 0, there is a delta bigger than 0 such that when a is less than x less than a plus delta, the absolute value of f of x minus L is less than epsilon. So notice that these two definitions, they're pretty similar to what we said about the precise definition of a regular two-sided limit. The difference here is that we're only considering values of x on one side of this point. We're either only thinking about when x is smaller than a, or we're only thinking about when x is larger than a. One of the immediate consequences of this is the following equivalence. And this sort of leads us to one of our first limit laws. Now, it won't seem so interesting or useful in itself for the moment, but we're going to see it's actually quite useful in a little while. So, theorem, having the limit as x approaches a, f of x be equal to L, this is equivalent to saying that the limit as x approaches a from the right of f of x is equal to L, and the limit as x approaches a from the left of f of x equals L. So if the limit exists and it's equal to L, then the right and left-hand limits both exist and have to be L as well. If we know the right and the left-hand limits exist and they're equal to L, then the limit has to be L and thus exist too. Okay, so the reason that this is useful is because, as we will see, there are situations where we can easily compute left and right-hand limits separately, but maybe computing the limit itself might be a bit tricky. In those cases, what this tells us is actually we can just deal with the left and right-hand limits separately and then ask what happens, are they the same number? Do they both exist and are they the same number? Notice, by the way, that implicit in this is that both must exist. Now, your textbook lists that they exist as a separate requirement. To my mind, that is not a separate requirement, okay? It is part and parcel of the fact that the limits are equal to L. They actually have to exist in order for that statement to make any sense, okay? So their existence is assumed if this, if it's equal to L, among other things, it exists. That's one of the things that needs to happen if you're going to be equal to a given quantity. You have to actually exist. Okay. Now let's talk about some other properties that we can find for limits. So here is one important property for limits. If f of x is equal to g of x, except at finitely many points, then for any value of a, the limit as x approaches a of f of x, and this is true for the right and the left-hand limits as well, has to equal the limit as x approaches a of g of x, or else both do not exist. What's important about this is it tells me if I have two functions and they're identical except at a finite number of points, I can work with whichever function is more convenient for me to use and calculate the limits for the easier one, and I know that it's the same as the limit for the more complicated one. This is going to be really important for us, and we're going to keep on making reference to this fact about limits as we continue talking about them. I apologize. This does not look much like a G. Now, the other thing that I want to observe here is, like I said, this is true if we're talking about from the right as well. It would also be true if we were talking about from the left. So, all three cases, I'm not going to literally rewrite this thing 3 times, though, just to take care of the little plus or minus symbols there. So just know that it is all 3. So that is our first limit law. And how do we prove that this is true? Well, the point is that what we do is we restrict delta to always be small enough that when 0 is less than absolute value x minus a less than delta, f of x is actually just always equal to g of x. And we can do this because there's only a finite number of places where these two things don't agree. So we can always just take our delta to be smaller so that within this interval, they agree on all of this interval except maybe at the point A. But once we do that, then delta either works for both f and g, or neither. Strictly speaking, I should say then for a given epsilon, delta will either make this work with the definition of the limit, or it only works, or it doesn't work for either of them. If it works for one, it automatically works for the other. So if we can find a delta that works for f, that delta automatically works for g. If we can find a delta that works for g, it automatically works for f. And that is why this works. This no longer works if they disagree potentially an infinite number of points. Then we can no longer do this, because then we cannot necessarily restrict our delta choices to be sufficiently small to make this work. So you can't do this in general for 2 different functions, which is a good thing. Otherwise, all limits would just be the same. But you can, as long as they just disagree at a finite number of points. And in particular, if they just disagree at A, then it doesn't affect the limit at A. So that is our first important property. The next property, and this one is fairly easy to see, is the limit as x approaches A of a constant k is always just equal to k itself. Now, how do we see that this is true? Well, the point is, given epsilon bigger than 0, let delta be equal to 1. When 0 is less than the absolute value of x minus a is less than delta, which is equal to 1, the absolute value of k minus k is equal to 0, which is less than epsilon. And so in this case, it's actually very straightforward by the definition to see that this has to be true. The next thing that we can see, and this is hopefully something that you will have already kind of proved, is the limit as x approaches a of x itself is equal to a. Well, let's just very quickly sketch how you see this. Given an epsilon bigger than 0, let delta equal epsilon. Then when 0 is less than absolute value of x minus a, is less than delta, which is equal to epsilon, absolute value of x minus a is actually less than epsilon. But this is my function and this is my limit. So therefore, we have established this fact. Now, so far, we've just been calculating a couple of limits here, or not really even calculating, but proving them using the definition. But now we get into where things become really interesting. So, suppose the limit as x approaches a of f of x is equal to L sub f, and the limit as x approaches a of g of x is equal to L sub g. Then the limit as x approaches a, f of x plus g of x is equal to LF plus LG. How do we see that this is true? Well, given an epsilon bigger than 0, there is a delta F and a delta G such that when 0 is less than the absolute value of x minus a is less than the minimum of delta F and delta G. In other words, we take these two and we take the smaller of them. We have absolute value of f of x minus LF less than epsilon over 2, and absolute value of g of x minus LG less than epsilon over 2. Now notice, I didn't just do epsilon, I did epsilon over 2. That's really important to notice. It's a really crucial step here. But I'm allowed to do that because I can find these deltas for any given value. It doesn't have to just be the given epsilon. I could take the epsilon you give me and cut it in half, and I can still find a delta that will make this work. Well, if this is true, then the absolute value of f of x plus g of x minus LF minus LG, this is going to be less than absolute value of f of x minus LF plus absolute value of, I'm writing the wrong thing here, absolute value of g of x minus LG. And that is going to be equal to, or actually I should say this is going to be, this is less than or equal to, this is strictly less than epsilon over 2 plus epsilon over 2, which is epsilon. So what we can do is we can take our delta to be the minimum of delta F and delta G, which I need to write down up here. We take delta to be the minimum of the given delta F and delta G, and then that is a delta that works for this epsilon, because here we have F plus G minus LF plus LG. So we have now established that if you add two functions and if their limits exist separately, then the limit of their sum exists and it's just the sum of the limits. Be careful here because it doesn't work the other way. You could have two functions that separately don't have a limit, but when you add them, you get something that does have a limit, okay? So it's a bit weird, but yeah, that kind of thing can happen where F and G separately, they don't have limits, but F plus G might have a limit. Now, that is the first of the really important limit laws here. Well, actually, it's not the first. I guess we've already done a couple of the important limit laws. But this is one of the first limit. It's the first limit law involving arithmetic. And it turns out that the other behaviors of limits under arithmetic are really just kind of the same idea, the same sort of thing of what you would expect. So, if the limit as x approaches a of f of x equals LF, and the limit as x approaches a of g of x is equal to LG, then what we just established is that the limit as x approaches a, f of x plus g of x, is LF plus LG. By an almost identical sort of proof, we can show that the same holds if I subtract them instead of adding them. So if I do the limit as x approaches a of f of x minus g of x, that's just the limit of f minus the limit of g. The same kind of thing holds for multiplication. So the limit as x approaches a, f of x times g of x, this is equal to the limit of f times the limit of g. Now, the proof for this one, I'm not going to go through it, but the proof for this one is just slightly more complicated than the one for addition and subtraction. We have to be a little bit more clever about picking our new delta, but we can do it. And that's the important thing. You can find a way to do it. If we were doing like an analysis class, because calculus is actually sort of basic analysis, the branch of mathematics called analysis. If we were doing a full-on high-level analysis class, then I would probably make you guys prove this as an exercise. But you are just doing a calculus class here, so I'm going to let it slide. If you're really interested in seeing the details, I'm happy to show them to you, but I think most of you will probably be content to just take this on faith. A fourth property that I do not have space to quite write here is that if LG is not equal to 0, then the limit as x approaches a, f of x divided by g of x, is just LF divided by LG. Now, you have to be careful here because if the limits of both of these things are 0, then their ratio might have a limit anyway, but you can't just find it by taking 0 over 0, because 0 over 0 isn't defined. So we have a little bit of a complication there that we have to deal with. So let's just take a quick look. Oh, and I should say before we take a quick look, all of those four properties, those hold for the from the right and from the left as well. So I wrote down the rules for regular, full, two-sided limits, as we call them. But in fact, they apply to the one-sided limits that only come in from the right or only come in from the left just as well. So let's take a look at some applications of this sort of thing. Let's suppose that we want to say the limit as x approaches 3 of f of x is equal to 4, and the limit as x approaches 3 of g of x is equal to 1/2. And we want to know what is the limit as x approaches 3 of f of x plus g of x. Well, the answer is we just take the sum. We take 4 plus 1/2, and that gives me 9/2. What about the limit of the difference? So x approaches 3. Let's do g of x minus f of x this time, just to kind of throw things up a bit. Well, this time I take the limit of g. This is going to be 1/2, and I subtract the limit for f, which is 4. So that gives me negative 7/2. What about the limit of the product? So the limit as x approaches 3 of f of x times g of x, well, that's just going to be 4 times 1/2, which is 2. And we can do the same thing with the ratios and everything as well, okay? So once again, it's not a big deal to kind of find these limits. I will leave finding the limit of the ratios there to you. Now, one of the applications of this that's very important is we can use these limit laws to tell us how to compute limits for polynomials. So if I have a polynomial, like let's say that I have, 5x squared minus 2x plus 1, and I want to know what is the limit as x approaches 2. Well, it wouldn't necessarily be obvious how to do this just from the definition, and proving it with the definition would definitely be really, really difficult. We could do it, it'd be hard. What we can do, however, is we can say the limits of each of these things are going to exist. So we can say the limit, assuming they exist, these are the limit as x approaches 2 of 5x squared plus the limit as x approaches 2 of negative 2x plus the limit as x approaches 2 of 1. This definitely exists, and it's just 1 because this is a constant. And this is going to be the limit as x approaches 2 of 5 times the limit as x approaches 2 of x squared. Then this is going to be the limit as x approaches 2 of negative 2 times the limit as x approaches 2 of x, and then we just have this plus 1. Now, this is a constant, so this just becomes 5, and this is going to be limit x approaches 2 of x times limit x approaches 2 of x. Then we're going to have, this becomes a negative 2, and this is just, the limit as x approaches 2 of x is just going to be 2 itself. And then we have plus 1. Well, this is also going to be 2, and this is going to be 2. So this becomes 5 times 4 times 4. Why did I say 4 times 4? 5 times 2 times 2, because I can actually, say that 2 is equal to 2, not 4. Then we're going to have minus 4 plus 1. Well, this is 20 minus 4 plus 1, which is 17. But notice that what we ended up doing was actually just seeing, we plug in the value x equals 2 into this polynomial, and that's what we get. Because as I broke this thing down, I was able to bring out the coefficients and eventually just show, well, the limit as x approaches 2, I split this up. The limit of x squared is just the limits for x multiplied together. In other words, the limits squared. So we ended up just plugging in 2 into this polynomial. And we got 5 times 4 minus 2 times 2 plus 1. Yep, that's 17. If you do an identical argument, you can show that every polynomial can be computed just by evaluating it. The limits for any polynomial, I should say, can be computed by just evaluating it. So what we do is we can say that the limit as x approaches a of x to the n, well, this breaks up into the limit as x approaches a of x raised to the nth power, which is just a to the n. And then we can say the limit as x approaches a of k times x to the n. Well, this is equal to the limit as x approaches a of k times the limit as x approaches a x to the n. This is just k times a to the n. And then we use the sum law that we wrote down before for limits. So that's the rule that says that the limit of a sum is the sum of the limits. It's sometimes called the sum rule. And then the others are called the product rule, the quotient rule, and then there's the difference rule for subtraction. Do note these are the sum, difference, product, and quotient rules for limits, because we're going to talk about other rules later on that are also called sum, difference, quotient, and sum, difference, product, and quotient. Those are going to apply to a different procedure, not to limits. But at this point, we see that the limits of monomials, we can find those by just evaluation. Well, from the sum law, this means that we can find the limits for polynomials by evaluation too. So, if p of x is a polynomial, then the limit as x approaches a of p of x is just p evaluated at a. Now, this is kind of a good thing. In this, when I say it's a good thing, I mean this kind of makes sense. If this didn't work out this way, we would probably want to rethink what we're doing. And the reason for that is because we expect that polynomials don't do a lot of bouncing around. They kind of go on in this nice continual manner. And so wherever we're heading, that's where we should get. The limit is kind of where is your function heading towards, and the value of the function, that's where you end up. Well, polynomials should always end up where it looks like they're going, so to speak. And that is exactly what this is saying. So this is another one of our limit laws. Now, it's not one of our sort of fundamental limit laws. It's not one that we need to go back to the definition in order to prove. It actually follows from our limit laws for sums, differences, products. We don't actually need quotients yet. And now that we have this limit law for polynomials, we can actually say the same thing is true for rational functions in most cases. So, if p of x and q of x are polynomials with q of a not equal to 0, then the limit as x approaches a, p of x over q of x, is equal to, well, this will be just p evaluated at a divided by q evaluated at a. The reason we can do this is because we can take these limits separately as long as the limit of the denominator isn't 0. But that's what this condition guarantees, because this q is a polynomial. Q of a is not equal to 0, so its limit isn't 0. And since the limits of polynomials come from evaluating, we just evaluate the top and the bottom, and we're done. What you got to be careful about here is making sure that your denominator isn't 0. Okay, so that's where we need to be careful. So let me show you an example of working with this stuff and where we need to be careful, and then what we can do if we do have a denominator of 0. So let's suppose I want to find the limit as x approaches 1 of, let's say, x squared minus 3x plus 3 divided by x minus 2. Well, the first thing to do is to notice if I just plug in 1, the denominator doesn't become 0. So I can just find this whole thing by evaluation. I can say this is just going to be 1 squared minus 3 times 1 plus 3, all divided by 1 minus 2. That's going to become 1 over minus 1, and my answer is negative 1. So I found this limit just by evaluating this thing. And you can see here how much easier this really is than if you were trying to mess around with the original precise definition of a limit, I hope. Because if we were doing the precise definition of a limit, this would be an absolute nightmare to figure out. Like, I have no idea what the delta would be for any given epsilon here. But our limit laws say you can actually find such a delta, and we don't need to show you what that delta actually is, as long as we can prove that there is one out there somewhere. Now, we could, if we spent a long time thinking about it, we could figure out what that delta value would be for a given epsilon. But we're not going to do that. The limit laws guarantee that it exists, and therefore, this is what the limit is. Now, here's where things get tricky. What if, instead of doing the limit as x approaches 1, what if we changed this around and did x approaches 2? Well, this time I cannot just do evaluation, because I would have 2 squared minus 3 times 2 plus 3 over 2 minus 2. And this would become, did I write this down incorrectly? I have this terrible fear now that I wrote something down incorrectly. X squared minus 3x Why is this not working out? Give me a second here while I double check and see why I'm going crazy all of a sudden. This is why. I wanted this to be a +2, not a +3. It doesn't change the previous example, but for this example, I definitely want that to be a +2 and not a +3. My apologies. I messed up when I was writing down the example that I had in mind and got one of the numbers wrong. Let's suppose that we want to do this one. So what we end up with here is 0 over 0. Now that's not defined, but also we can't use the evaluation technique here because we have a 0 in the denominator. Here's what we can do. What we can do is we can say that x squared minus 3x plus 2 over x minus 2, this is x minus 2 times x minus 1 divided by x minus 2, and that is just equal to x minus 1 except at x equals 2. But as long as two functions are identical, except at one specific point, I am allowed to work with whichever one is more convenient. And this one is more convenient. So what I can say is this must be equal to the limit as x approaches 2 of x minus 1. Well, that's just going to be 2 minus 1, which is equal to 1. And there we go. We're done. In fact, if you can cancel things out, you make the evaluation process simpler no matter what. Now, let me just go back really quickly and show you if I'd left that as a 3, what would have happened? Well, if this had still been a 3, like I accidentally wrote down to start with, then when we did the evaluation, we would have had 2 squared minus 3 times 2 plus 3 divided by 2 minus 2. This would have come out to be 1 over 0. When the numerator is not evaluating to 0 and the denominator is, then this limit is going to does not exist. The only way the limit can still exist if the denominator is 0 is if the limit of the numerator is 0 as well. So in that case, we would just be done, and this original limit does not exist. But the upshot of all this is we can use our rule that says changing a function at finitely many points doesn't change the limits. We can use that to say, I can cancel any factors that I want to that are common to the numerator and the denominator, and it doesn't change the limit. So let's take a look at another example of doing that. Let's suppose that I want to do the limit as x approaches minus 3, and let's see if I can actually make this example work this time. Let's suppose that I have x squared minus x minus 6, and then on the bottom I have x plus 3. If you go ahead and you try to do the evaluation, you'll see that this becomes 0 over 0. Because, does it become 0? Did I mess up the sign again? 9. Yes, I messed up the sign again. Wow, I'm doing really poorly here on this sort of thing. So, I know exactly why I messed up the sign. What I meant to do was x squared plus x minus 6. There we go. Now it works. Because now I would get 0 over 0. So I would have negative 3 squared. That's 9 minus 3. And then minus 6 brings me to 0. So this ends up giving me a 0 over 0 when I evaluate it. And what that tells me is I want to look for something that I can cancel. So what I can do is I can say this is the limit as x approaches negative 3 of x plus 3 times x minus 2 divided by x plus 3. I can cancel the x plus 3s. Now, you got to be careful when you cancel things because you are in general changing the value of the function at a certain point. In fact, what we are doing is we are creating a function that has a slightly larger domain than the original function. The domain of this thing does not include negative 3, but the domain of this guy does include negative 3. But at this point, we can find this by evaluation. Negative 3 minus 2, and we get negative 5. There we go, we're done. This kind of technique, this is actually one of the main motivating factors in looking for limits, because remember, one of the things that we were interested in when we looked at kind of the problem that motivated us in some ways was this: what happens to the average rate of change as my 2 points, my starting and my ending point, get closer and closer together? In other words, what happens to the limit as b approaches a, f of b minus f of a divided by b minus a? Well, the hope is that this will come out to be something that looks like a 0 over 0 problem. And then what I can do is I can try to mess around and cancel things and see if I can make sense of this kind of thing. See if there's a way to cancel stuff off and extend this quantity naturally to the case where b is equal to a. So we will come back to dealing with that kind of thing, but for now I want to mention one other sort of thing that happens that we need to worry about. And that is, what if we are dealing with left and right hand limits separately? Or when do we really need to deal with left and right hand limits separately? Well, the answer is we often need to deal with left and right hand limits separately if the definition of a function changes at a given point. So for example, let's suppose that we can find, if it exists, the limit as x approaches 1 of f of x, given that f of x is going to be equal to, let's suppose that it is equal to x plus 3 when x is smaller than 1, and then it's going to be equal to 4x when x is bigger than 1. Problem. I can't just take the limit because this is not just a polynomial. But what I can do is I can split this up into 2 different cases. So what I can do is I can say, well, as x approaches 1 from the left, on the left-hand side of 1, this function is just x plus 3. So the limit as x approaches 1 from the left is the same as the limit of x plus 3 from the left. And that I can find by evaluation. It's 1 plus 3 equals 4. Okay, so there's that part done. If I came in from the right-hand side, I can say the limit as x approaches 1 from the right of f of x, this is the same as the limit as x approaches 1 from the right of 4x, and that is just 4 times 1, which is 4. So both of these exist, and they are the same. That means my original limit comes out to be 4. So here's the basic rule when you're dealing with piecewise defined functions like this. You look at your limit. If the place where you're taking the limit happens to be in the middle of one of the intervals, then you just use whatever function whatever expression you have on that interval. So for example, if I wanted to do the limit as x approaches 0 of f of x here, well, I would just use the x plus 3, because near 0, x plus 3 is the definition. So this would just be the limit as x approaches 0 of x plus 3, and that's just going to be 3. But if it is at a transitional point where we switch from one definition to another, and it doesn't matter if one of these has a strict and non-strict inequality, it does not matter. It's a transitional point, we still have to do this. We then have to break this into what happens to the one that's coming in from the left versus what happens to the one coming in from the right. So let me show you another example of doing this kind of thing. Let's suppose that I want to find the limit as x approaches -2 of g of x, given, here's my g of x. So this is going to be a piecewise defined function, and we're going to have 2x minus 1 for x less than or equal to -2. We are going to have, let's say, x squared for x -2 less than x less than or equal to 3, and then we'll have 3x plus 2 for x bigger than 3. here's what we're going to do. The negative 2 is a transitional point here. We change from 2x minus 1 to x squared. So we split this into the limit as x approaches negative 2 from the left. That is going to be the limit as x approaches negative 2 from the left of 2x minus 1. And that is going to be 2 times negative 2, that's negative 4, minus 1, I get negative 5. And then we're going to do the limit from the right. So we're going to do the limit as x comes into negative 2 from the right of g of x. Now we need to be a little bit careful here. So take a minute to yourselves and think about which one of these do you think we should use? Well, the answer is I want to use the x squared. Eventually, we turn to the 3x plus 2 definition. But the immediate thing to the right-hand side of negative 2 is x squared. So that is the one that I want to focus on here. So I'm going to do the limit as x approaches negative 2 from the right of x squared. That's going to be negative 2 squared, which is 4. So the left-hand limits and the right-hand limits, they both exist, but they're different numbers. They differ from one another. That means that this original limit does not exist. If we looked at a graph of what is going on here, what we would see graphically is that as we come in from the left-hand side, we're going to have this, and I'm just going to sketch a little piece of this graph, but we would have this kind of thing coming in from the left, and then to the right of that, we would have the start of this parabola. So what's going on is from the left-hand side, we come in towards negative 5. From the right-hand side, we come towards positive 4. We're going to different places like this. And so there's no single value that we approach on both sides. All right, so I'm going to end things there for you guys today. And next week, we will talk about infinite limits and limits at infinity. So I will see you guys then.